Good morning, everyone. I'm Sungkyu from Building Informatics Group at Yonsei University, Korea. Our research focuses on enriching BIM models with semantic information, in particular, material layers using annotations from CAD drawings. While the paper we submitted covers only a part of a process, today I will present the full scope of our work. To begin, I'll give a quick overview of the background. A review of the past 5 years shows that while geometric reconstruction has improved, semantic information is still lacking. However, material layer information, a key part of architectural meaning, has been largely overlooked. To address this gap, we aim to enrich BIM models with semantic information by using material annotations from section drawings. We propose a method to generate BIM objects that include detailed material layer data. However, there are 4 main challenges in processing material layer annotations. First, text annotations are often obscured by other drawing elements. Second, it's unclear what function each material layer serves, yet this is required by BIM authoring tools. Third, the annotations are stored as individual vectors, so the computer cannot recognize which ones belong to the same set. Fourth, it's not obvious what building object type the set refers to. Next, I'll explain how our method works. The method we propose consists of 4 main steps. In the semantic clustering step, we use a coordinate-based clustering algorithm. It groups material layer annotations in the CAD drawing into sets based on their spatial positions. The material layer function assignment step classifies the function of each material layer. We use an LLM with a new technique called horizontal-driven prompting. This method improves performance by collecting common errors and helping the model better understand architectural context. Next is the classification of building object types. We still need to infer what type of object the layer cell represents, such as wall, slab, or ceiling. Previous studies mainly relied on geometry or spatial relationships. In contrast, our method uses only material layer data and a pre-trained LLM to classify object types in a simple and effective way. We guided the model using a fuchsia prompt with 3 examples. Finally, we generate semantically enriched BIM objects using the processed material layer information. Using the BIM authoring tools API, we create compound objects that contain multiple material layers on top of the geometric model. Here is an example and the data flow of our method. First, we start with material layer annotations for a wall, as shown on the left side of the figure. Through semantic clustering, individual annotation vectors are grouped into a single material layer set. Next, we classify 2 key information, the function of each layer and the object type of the set. Finally, using the BIM authoring API, we generate semantically enriched BIM objects. Before we go into the results, let me show you a short demo video of our method. The material annotations in the CAD drawings are as follows. When a drawing is uploaded to our web app and the process button is clicked, the system automatically infers the necessary information. The output is then generated in a format that works with BIM authoring tools. As you can see, the initial BIM model contains only default families. However, when the process CSV file is imported into Rabbit through our custom add-in, it generates new families that reflect the material layers from the CAD drawings. Finally, to semantically enrich the geometric BIM model, these generated families replace the geometric objects based on predefined rules, completing the process. Next, I will explain the experiment phase of our study. We tested each step by comparing different models. The experiment was conducted using real design data from 9 projects in North America and South Korea, including 90 CAD section drawings. To ensure fair evaluation, we used BIM models from 20 separate Korean projects to create prompts and fine-tune the machine learning models. In step 1, we evaluated clustering performance using the adjusted land index. Among the tested methods, K-means clustering achieved the best result with an average ARI of 99.9%. In step 2, we used weighted F1 square and macro F1 square to handle data imbalance. The best result came from our correspondence-driven prompt combined with GPT-01, achieving a weighted F1 score of 99.5%. In step 3, we again used weighted F1 score and macro F1 score to handle data imbalance. We found that LLM-based classification outperformed traditional machine learning models. Among them, GPT-01 achieved the best performance with a weighted F1 score of 92.7%. In step 4, we evaluated object generation using accuracy. Using the process data, we generated 19 BIM objects from 2 projects, achieving 100% accuracy. Since this step is rule-based, it can be also applied accurately to the remaining 7 projects. Now let me conclude the presentation. First, here's a brief summary. This study aims to semantically enrich BIM models using material layer information from CAD drawings. To do this, we proposed a 4-step method using K-means clustering, LLMs, and the BIM API. Here are the main contributions of our study. First, we address a gap in the 2D to BIM research field by covering material layer information, which has been largely overlooked. Second, to deal with the common lack of material layer function data in CAD drawings, we propose a novel technique called correspondence-driven prompting. Third, we introduce a lightweight object type classification method that uses only material layer text. Lastly, let me share some limitations of our study. Our method was demonstrated using walls, slabs, and ceilings. However, we believe it can be extended to other building elements as well. Thank you for your attention.